To begin this second part of our free body diagram lecture, we're going to discuss the other three types of free body diagrams that we commonly see in physics. First, we'll talk about Atwood machines, which are going to be scenarios in which we have a pulley and two masses, and we think about what happens to these masses as they're allowed to freely flow through the pulley and kind of through the system themselves. Over the edge style problems, which we think about, maybe I have a cart of some sort, we have a pulley involved again, and possibly have a mass down here, and what happens to the acceleration when this system is released. And then finally, ramp problems, which are used oftentimes to discuss possibly a bicycle biking up a hill, moving something up a ramp, what would be happening in these scenarios and where the force is acting on this object, possibly as it's moving up, or quite honestly even down a ramp, and kind of where the force is acting on that object. And in particular, for at least these first two, I really want us to take a step away from the math that's associated with these problems and think about them a little more conceptually. So first, let's grab a new slide and let's talk about Atwood machines. So for Atwood machines, let's see if we can find not only the acceleration of the machine itself, or of the system, but then also the tension on the string. So Atwood machines, it's basically a pulley system where we have a pulley, we have mass A, we have mass B, and mass A is meant to look larger in this scenario so that we can begin discussing its acceleration. Now, if you recall from last year in honors physics, you may have been faced with a scenario in which you were doing some canceling out of tension, and so that's how you found your acceleration value. But I would rather, let's focus on the conceptual side of all of this. We know that we've got a mass of 30 kilograms for object A, a mass of 20 kilograms for object B. So I'm going to ask you two questions. What is causing the motion, or what is going to be causing motion to take place in this system, and then what is attempting to slow it down, or what is hindering that motion that's being caused in this example problem. So again, those two questions: what is causing the motion, and then what is slowing that down? Let's think about those first as really our system and what we're going to do within our system. Well, we know that we're going to be thinking about the sum of the forces. Now, the sum of the forces is going to be either in the horizontal or the vertical. And let me give you a second to think about this one. Is our motion horizontal or is our motion vertical? Hopefully you said that our motion is vertical. That's why we're going to give it the Y notation. And we know that we're going to have two real forces acting on the entire system here. Not just the objects by itself, but the entire system. Those two forces acting on the entire system in this example are going to be the weight acting on object A and the weight acting on object B. Now let's think about our first questions here. What is causing the motion? Well, object A is larger. So really, object A is going to be what's initiating the motion and giving us an acceleration in this direction. So object A is going to be one of the main forces in the sum of our forces, the weight of object A. Well, what's trying to slow that force down? What is resisting that motion? That's going to be object B. So the weight of object B can be subtracted. Now, you may at this point say, but wait, what about the tension? Well, the tension is going to be a counterforce within the system. So yes, there's going to be tension on this rope right here. Yes, there's going to be tension on this rope right here. But we are not necessarily concerned with that tension right now because those are going to be within the system. Newton's third law is an object in motion stays in motion unless acted on by an outside force. Technically, in the example we're talking about right now, the string itself is an internal force. It's not important, and it doesn't need to be discussed when thinking about just the motion of box A and box B together as a system. Where the tension will become important is when we think about just box A or just box B and the motion that's contributed to just box A or just box B. But we're not quite there yet. So if you just go, huh? Listen to that little stipulation that I just talked about a couple times. And then when you're ready, what we're going to do right now is we're going to talk about the motion of this entire system. Right here, this entire system as a whole. So we have the sum of our forces. The sum of our forces, and that is very difficult to read. The sum of our forces in the vertical. That's going to be equal to the weight of object A minus the weight of object B. Why are they subtracting? Because object B is slowing object A down. Well, and I should say object B is slowing down the motion that was caused by object A. So let's do a little math. Let's find the weight of object A and object B. So the sum of our forces in the y direction are going to be equal to, well, A is 30 kilograms, so 30 times 9.8 minus 20 times 9.8. Well, without having to do too much simplification, we're going to see that that is going to be equal to 98 newtons. Okay, well, you may say, okay, what does this tell me? What can I do with this piece of information? Well, I'm going to scroll down just a little bit here. And don't forget that the sum of the forces, F is equal to ma. And in this example, we're talking about the sum of the forces in the y direction. So we're going to have an acceleration that's also going to be in that y direction. Okay, so now if I'm going to solve for acceleration, and let me pick a different color for this next part, what we're going to see is 98 is equal to the mass of all the system. Well, let's think about this really quick. We're talking about the entire system here. Remember this big line we circled right here? We're talking about this entire system. So that means that we need to be talking about the mass of object A plus the mass of object B multiplied by the acceleration in the y direction. And now you might be saying, wait, why is it now that you add these? Why before did you subtract these? Great question. Now what we're thinking about is we're thinking about the sum of all the forces, and we're using the equation F equals ma. And now we have to think of the mass of the entire system. So let's pick a different color for this. Now we're thinking about the mass of the entire system. Nothing's acting against each other because we're thinking about the system as a whole. So we have to actually add these values up. So we have 98 is equal to 50 kilograms, and I got that by taking 30 plus 20. 50 kilograms and multiplying it by the acceleration in the y direction. Now let me scroll down just a tiny bit here. What we're going to see now is that our acceleration in the y direction is equal to 1.96 meters per second squared. So that allowed us to find the acceleration of the system as a whole above here. Oops. When we think about the acceleration of the system as a whole, we see that the acceleration of block A and block B as a whole is going to be 1.96 meters per second squared. Well, now we can actually find the tension. So let's take a step back and let's consider both of these objects as separate objects. And for this, I'm going to move to a new slide and redraw this picture. All right, so now we're looking at a very similar picture than the one that we just drew, or the example that we were just talking about. And instead of considering what we considered before, the entire system of this entire motion, now I'm going to jump back. We're going to think about just the motion of box A or just the motion of box B. So let's think about the motion of just box A for a second. For box A, what is causing that motion? Well, what's causing that motion is going to be, and I'm going to pause it here for just a second. All right, so if we think about box A and what's going to actually cause the motion to box A, we'll see that box A's motion, oops, let's not use the same color here. Let's go with a new color, something fun like orange. Let's say that box A's motion is really going to be caused by the weight of box A. And we know that the weight of box A is causing the motion because its mass is greater than box B. So what's resisting the motion of box A's motion? Well, box A's motion is being resisted by the tension on this rope. The tension on this rope is going to be what's resisting that motion. Let's jump over to box B. Box B is going to have the motion that's being caused. I'll let you think about this one for a second, remembering that it's going to be traveling upward like this. Let's pick a different color for that. Ooh, um, this green color looks fun. Our motion is going to be like that. So what's causing the motion? Well, the tension of the rope is causing that motion. So that tension in this direction is causing the motion. What's resisting the motion is going to be the weight of object B. The weight of object B is resisting that motion. That means if I continue this line down and I think about F net, or the sum of all the forces, let's stay consistent here. Let's say the sum, hey, the sum of all the forces for object A only, and we know this is in the y direction, are going to be the weight minus the tension. If we jump down to the sum of all the forces that are causing the motion for object B, again in the y because it's only vertical motion, we're going to see the tension minus WB for the weight for object B. Well, don't you forget, F equals ma. M is a value we know, A is a value we know. Well, same thing over here. Newton's second law works everywhere. So this is very helpful. Well, and don't forget, this is F net too, so this is really going to be the same thing. This is the sum of these forces in this direction. So what I can do is scroll down just a little bit, and I say let's choose object. Actually, let's choose object B. And for object B, I'm going to scroll down just a little bit more. For object B, I can actually take these two equations right here, and I like that highlighter. That's always fun. Highlighter. I'm going to take these two equations right here and make them equal to one another. Make these two equations equal to one another so that I can find tension, because I know the mass, I know the acceleration, and I know the weight. So all that would be the only unknown value there would be the tension itself. So let's do a little math now. All right, scrolling down just a little bit more. T minus the weight of object B is equal to mass times acceleration. All right, so T is minus, and then what is our weight for that object B? 196 newtons. So T minus, sorry, I paused there for a second and now I don't actually know where I was, but T minus 104 or 196 will be equal to the mass of object B, which I think is 20, let me scroll up. Yeah, 20 kilograms multiplied by the acceleration, which we found on the last page. I'm going to jump back quick, which is 1.96. Jumping back. Hopefully that doesn't make you sick when I do that. Multiplied by 1.96. All right, calculate it out. I'm going to do this just in real time, just for simplicity's sake. 196. And 196. I'm getting a tension value of 235.2 newtons. Let me check my notes, make sure that's right. Yes, it is right. Awesome. So our tension value right there is going to be the tension acting on just object B. Great news! The tension acting on object B, let's give ourselves a new color. The tension acting on just object B is going to be equal to the tension just acting on object A. These tensions will be same. And really, quite honestly, if you wanted to, you could go through and do this check math right here and do that for object A, and you will get the same tension value for object A as you would for object B. These values will be equal to one another when you calculate them out. All right, let's talk about a new style problem. We're going to go to a new slide. Let's talk about over the edge style problems. For this one, let's draw ourselves a little table. Let's draw ourselves a car. Give ourselves a pulley. Using a new color, let's have our object be pulled by this pulley. And oh, we got a big old box down here. All right, so looking at our over the edge question right here, what we want to do is first again think about this in terms of the entire system and answer those two questions before. What is causing the motion and what is resisting the motion? And based on the necessary or the given information we have here, we can find the acceleration of this system. So first of all, let's ask the question about the system. What is causing the motion? What is causing the motion? Well, the motion is being caused by, and let's use some arrows for fun this time. Let's give ourselves a fun color. The motion is being caused by the weight of object B, by the weight of object B. Once we release this system, the weight of object B is going to be causing the motion. Well, what is going to be resisting that motion? That motion is going to be resisted by the tension, by the force of friction of object A. So the force of friction of object A. And is this kinetic friction or is this static friction? Well, there's motion taking place, so it's going to be a kinetic friction value. So let's really think about this for just 1 second. Now, if we had to, we could identify a bunch of other forces acting on these two objects. And for fun, let's identify those other forces just really quickly. We know that the tension on the rope in that direction, that's a little light. Let's pick a different color. The tension on the rope is going to be in the opposite direction of our weight. The tension of the rope is going to be in the direction of the motion. We also know that we've got the weight of object A and the normal force of object A. So now, and again, we care about what's causing the motion, and this is really going to result in the sum of the forces that are causing the motion. And what's causing that motion is going to be the weight of object B. For this entire system, remember, not an individual block or the individual little cart A by itself, but for the entire system. So we see the sum of the forces are going to be equal to the weight of object B that's causing the motion. What's resisting the motion? Well, that's going to be the kinetic friction on box A, the kinetic friction that we see up here for box A, right here. This friction is going to be resisting that motion. Well, this is something we can already plug in numbers for. We know that the weight of object B, if we do a quick little math, the weight of object B is going to be equal to 30 multiplied by 9.8. We're going to subtract from that the force of friction. Now, in order to get the force of friction, it would benefit us to solve for the force of friction. So I'm going to jump over to the left-hand side. Remember that the force of friction is going to be equal to the coefficient of friction multiplied by the normal value, and that's going to be a kinetic example right now. So if we take the coefficient of friction is going to be equal to 0.04 290 multiplied by 294. So we are seeing that the force of friction is going to be equal to 0.04 multiplied by 294. And the value I get for the force of friction then, that's kinetic, is going to be equal to 5.88 newtons. So we can plug that in up here. Let's give it a new color. 5.88 newtons. Where did this number come from? Right here. Came from all this math over here on the left-hand side. To find the force of friction, we have to multiply the coefficient of friction by the normal value. So we find that the sum of all the forces, when I subtract those, is going to be 288.12 newtons. Now remember, F equals ma, that special Newton's second law, one of my best friends. Well, we can plug those numbers in now. And again, this is not just m by itself, but ma plus mb. And it would do us good to write that entire equation down. F is going to be equal to, this is really F net, is going to be equal to ma plus mb multiplied by the acceleration. And let's change that from F net to the sum of the forces. Those mean the same things. Don't get hung up on that difference there. F net and the sum of the forces mean the same thing right now because we're talking about the entire system. So now let's do a little plugging and chugging. Let's get a fun orange Halloween color. 288.12 newtons is going to be equal to 30 plus 15 multiplied by A. In the end, our A value is going to be equal to 6.4 meters per second squared. Woohoo! All right. So what I like about this model is it does not require you to do any kind of crazy canceling out, but just really kind of think about things conceptually. Here is our sum of our forces. What is going to be causing that motion? What is going to be fighting or deterring or resisting that motion? All right, now do a little plugging and chugging. Nicer, more comfortable math for us. Well, now that we have the acceleration value, we can treat this like two separate systems. Separate system for block A and for block B, and we can find the tension of the rope. I'm going to pull up a new slide and kind of set up the same picture as before, and then we can go through the math. So now, rather than thinking about this as a total system and thinking about block A and block B as a system together, we're going to break them down, and we're going to think about just block A or just block B, and think about them individually and what we've got going on. So let's think about block B first. Quite honestly, block B will be a little bit more intuitive, and then block A we can talk about. So block A, what's causing the motion? And let me write down a couple things for us. So first think about what's causing the motion for block B. Well, what's going to be causing the motion for block B is going to be the weight of block B. The weight of block B pulling down on it is going to be causing the motion. What's going to be resisting the motion of block B? Well, that's going to be the tension on the rope. All right, well, let's jump over to block A. What's causing the motion for block A? Block A's motion is going to be caused by the tension of this rope. What is going to be resisting the motion for block A is going to be the kinetic friction in the other direction, which we can write out as F of K. So if I want to, I can really think about the sum of the forces for block A. And really the sum of the forces are going to be the tension subtracted by the kinetic friction. And the sum of the forces in the block B are going to be equal to the weight minus the tension. Well, and don't forget that the sum of these forces can also be written as F equals ma. Sum of these forces can be written as F equals ma. And what we can do is make the, let's make that a b, is we can make these values equal to one another. So I recommend that it might be easier in this situation to pick block A. You can pick either one, block A or block B, but for fun, we're going to choose block A. So let's pick a new color just for fun. I like Halloween orange. Tension minus F of K is equal to mass times acceleration. Tension's what we're looking for, minus, what is that force of friction? We might have to look on the prior page. Just a second. 5.88. Where did I find that? Sorry for flipping around back and forth if it makes you sick. We found that force of friction right there. We make that 5.88. It's going to be equal to the mass of object A, which is 15 kilograms, multiplied by the acceleration. Prepare for it. I'm going to flip back over, which is 6.4. 6.4 multiplied by 6.4. And now we can solve for T. And I'm going to get a tension value of 101.88 newtons. And what you'll find is regardless if you did block A or block B, you're going to get the same tension value over here as you would over here, because the tension for A is going to be equal for the tension of B in both situations. And really it's the tension overall. You don't even have to write this A and B. It's the tension in both scenarios. All right, the last one I'd like to talk about are going to be ramp or hill type problems. They are the doozies of them all, but they're some of the best problems. So let's pull up a new slide and let's get ourselves introduced right away. So let's say that I have a ramp here, and my ramp, here's the ground, but my ramp is going to be up, and maybe we want to, well, it's okay that we have lines with arrows at the end of them. And we've got this ramp here that maybe, just maybe, there's an angle here of 10 degrees. Is that what angle I would like to use? Searching my notes, searching my notes. Yes, 10 degrees is what we'd like to put there. And let's say that I'm a bicyclist biking up a hill. Now, for all our free body diagrams, we're just going to draw a box. We don't need to be creative with our drawings. But in this situation, let's pretend I'm a bicyclist biking up a hill. And let's say that my force applied, let's give ourselves some information right away. Let's say that my force applied as I'm biking up this hill. Hey. So I'm biking up this hill. My force applied, oops, as I bike up the hill is going to be 550 newtons. All right, let's give ourselves one more piece of information, or a couple more pieces of information. Let's write down that the mass of myself and the bicycle, and obviously now I'm just writing in imaginary numbers, is going to be 250 kilograms. And then let's use actual real numbers, so give me just 1 second to find. So let's say the mass of myself and the bicycle is going to be equal to 70 kilometers. That's more realistic to a real example that we've got here. Now let's also talk about the coefficient of friction, and this is going to be kinetic friction because I'm biking up the hill and I am in motion. And let's make that value 0.06. Okay, and it's with this given information that I can actually solve for a lot of information, including my acceleration value. Now I've let this line here at the very bottom that's highlighted represent the ground, but I'm going to draw a few more lines, and so I'm actually going to delete it for right now, mainly because, and maybe I'm actually not going to really delete it. Let's see if I can delete that line. Because it's going to kind of get in the way of what I would like to do next, which is give ourselves an X and Y axis to really function with. So let's pick a line, and usually this is the one thing that really rocks people's world, so pay special attention to this. I'm going to allow this first line right here, that I'm just kind of redrawing over, I'm going to allow this line to represent my X-axis, and I'm going to allow myself to make this line right here my y-axis and attempt to make that line perfectly perpendicular for this situation. All right, so again, I'm biking up this hill. I'm biking at 10 degrees. I've given myself an X and Y axis here just for component sake, but now I can actually write in a couple values. Well, my force of gravity pulling down on me in this scenario is going to be straight down. And that's not bad. And a little tidbit of information here, the angle that we see right here is going to be 10 degrees. That's the same angle that we saw over here when we had the ground right there, which we're just kind of ignoring the ground right now. So that same angle is 10 degrees. And our force of gravity is still going to be our weight. So really, this is going to be our weight right here. And if we find our weight of our object, and really this is the weight of myself and the bicycle as I'm biking, our weight is going to be 686 newtons. Now, what we want to do right away is we want to find the x component and the y components for this weight, because this weight that we see coming straight down, this is the kind of the applied weight, the force of gravity working on me. But now I want to find, let's use fun colors. Now I want to find the force of gravity, and actually let's turn that around. The force of gravity in the x component. So the weight in the x component. And then I also want to find the weight in the y component, which is already, there's already a dotted line drawn here, but we'll draw it again. Ah, there you be. And that's going to be our weight on the y component. So let's find those doing some right angle trig. And remember, there's no shame to your game if you gotta write SOHCAHTOA over here, alright? And really you can get away with just writing SOH and KA. And what we're gonna find is that the x component is going to be our sine of our angle, which is 10 degrees, multiplied by 686. And our y component is going to be our cosine of 10 multiplied by 686. Well, let's calculate that out. So we're going to see that our force, or our weight in the y value, is going to be 119.1, or we'll just leave it at 119 newtons, and that our force in the x value is going to be equal to, oops, sorry, our force in the y component, of course that would happen, our force in the y component is going to be 675.6 newtons. And let's draw that other thing really quickly. I mixed up my computations here on my calculator. And my value for my force, or my weight in the x component, is going to be 119. Sorry for that little mix up there. Now, before we go any further, let's scroll down, give yourself maybe like 4 lines, and let's take a second and let's think about this. We want to think about the sum of all the forces acting on the bicycle as it bikes up the hill, and what's really kind of considered the x direction right now. We're considering, oops, we're considering this line right here, right here, this line. We're considering this to be our x direction. So if we jump back down, we're thinking about the sum of the forces in the x direction. And this is going to be the force applied by myself as I bicycle up the bike, subtracted by the forces that are slowing me down. One force that's slowing me down is going to be the force of friction, kinetic force, because the object is in motion. But another force is going to be the force of gravity, or the weight in the x direction. And that's really attributed to the steepness of my hill. The steeper the hill, the greater the weight in the x direction value. The less steep the hill, the smaller that value. And obviously if I was going downhill, this value would be helping me and actually helping me move down the hill quicker. and would be very useful in that situation. Well, if I'm thinking about this sum, and remember, this is going to let me do F equals ma here in a little bit. Let's see, I know the force applied from above. That's going to be 550 newtons. Oops, 500 or 550? 550 minus the force of friction. Whoa, wait a second. I haven't gotten that value yet. Let's jump up a second and let's think about that force of friction. Force of friction, remember, is equal to the coefficient of friction multiplied by the normal value. Do I have a normal value yet? I don't. Well, just pay attention to this next part. Our normal value is always going to be equal to our weight for our value. Now, we have to think about weight, though, as being the value that's perpendicular to the surface that the object is making contact with. So we're talking about the area that's perpendicular to our floor or to the surface that we're making contact with. Thus, the normal force is really going to be in this direction right here. Do you see this line I'm drawing right here? Whoa, whoa, whoa. This right here is going to be our normal force because it needs to be perpendicular to the surface. And what we're going to see, oops, what we're going to see is our weight in the y is going to be equal to our normal value because this is going to be the weight in the y is going to be the force that's being applied down onto the surface perpendicularly, and then our normal force is going to be kind of like the response or the paired force that's going to be pushing up in that perpendicular direction. So let's actually solve for our force of kinetic friction. That's going to be let me jump to the next page. Somewhere we solve for that. Where did we solve for that? Oh, 0.6, 0.06, sorry, multiplied by our normal value, which is going to be equal to our value for our weight in the y, which is going to be equal to 675.6. All right, we'll multiply those quick, and I'm just going to do this in real time. 675.6. I hope you guys are doing this in real time too. All right, I'm getting the F of K value equal to 40.5 newtons. Okay, so we can jump back over then and add that value right over here. And let's pick in a new color. So we're going to add this value right over here, 40.5 minus, I'm going to scroll up just a slight bit, our weight in the x value. Remember, this is attributed to the angle that we're biking up this hill, and it's slowing us down. So let's plug this in, 550 minus 40.5 minus 119. The sum of the forces in the x are going to be equal to 390.5 newtons. Well, last thing for this whole adventure is we can use this information to find the acceleration as I bike up the hill. So let's use Halloween orange. Let's remember that the sum of the forces in the x are going to be equal to mass times acceleration. Well, we already know the sum of the forces in the x. We know that that's 390.5 newtons. We know the mass of myself and the bicycle. It's 70 kilograms. And we can multiply that by a to solve for our final acceleration. And well, what'd you get? You get an acceleration value of 5.58 meters per second squared. I hope you did. All right, and this concludes going through all the examples of free body diagrams. Whew. all of those examples. If you have any questions, please ask Mr. Culligan or myself for help. Hopefully these will help you with your reading. A reminder that your reading is like page 101 to 112. I don't have the book right in front of me, but then you should also go through those example problems over the course of the next 10 pages, quite honestly. So that's going to be like 112 to like 119, 120, somewhere around there. We'll be talking about examples of all these free body diagrams in class, but hopefully this is giving you a really good background knowledge to just rock this out. That was a fun 40 minutes worth of physics, wasn't it?